These are on page 304 in your textbook. There are formulas for cylindrical shell, which is, I mean, I guess my water bottle isn't a bad example of that because it's a cylinder, but this wall is very thin if it's empty. If the thickness of the shell is negligible compared to the radius of the cylinder, then you can call it a cylindrical shell. Solid cylinder is, solid. If this was filled in with plastic all the way through, that would be a solid cylinder. There's a spherical shell like a globe, although a globe also has like metal thing running through. So pretend you take a globe off its stand. That would be a cylindrical shell. Solid cylinder. Most planets can be, well, not gas giants, I guess. Rocky planets and moons and stuff can be approximated as solid spheres. Sorry. A rod axis through the middle, so that's something like a pencil. Your axis through the middle. Pretend the pencil's uniform. This is for an axis through the end. So if we're rotating like this, is rod end, rod mid. It's rotating like this. Hollow cylinder. So this is different from a cylindrical shell. This is where the thickness of that outer wall is not negligible. And then a rectangular prism. So if you take like the sheet of paper is your object, but then it has non-zero thickness. That's the moment of inertia for this, or even a flat sheet too. It's the same if you have an axis passing straight through the middle. So you'll use some of these formulas on the homework, and we'll derive some of them next class. Yeah, and you might notice for a solid cylinder, for example, the mass would be distributed over this cylindrical shape. So the average distance of the mass is, somewhere in the middle. Whereas for a cylindrical shell, the mass is all a distance r away from the radius. And you notice that the solid cylinder, the fraction is smaller. That's 1/2. This is 1. So if they have the same mass and radius, a cylindrical shell will have a bigger moment of inertia than a solid cylinder. However, if they're made of the same material, then they won't have the same mass, right? The one that's solid will have a much greater mass. And the one that's solid will have a bigger moment of inertia. It's the same material, because the solid cylinder would be like the cylindrical shell, but then with more stuff added in. Anyway. So if you have the same net torque exerted on a solid cube and a hollow cube of the same mass, which experiences greater angular acceleration, well, we know net torque equals I alpha, so the operative factor is going to be the moment of inertia. If they have the same mass, and I didn't say this, and the same dimensions, I should have stated that here, that they have the same dimensions. Well, all that's different then is where the mass is located. So the hollow will have a greater moment of inertia because the mass is farther from the axis of rotation, so the solid will have greater alpha. Based on the equation, we can see that angular acceleration is inversely proportional to the moment of inertia when you have the same net torque. Which would have greater moment of inertia, solid sphere rotated around the middle or rotated around the edge? Well, think about it. Got your solid sphere. This is your axis passing through the middle versus solid sphere axis passing through edge. Well, on average, which has mass closer to the axis of rotation? This one's going to have mass closer to the axis of rotation. This one's going to have mass farther from the axis of rotation on average. So the axis on the edge will have greater moment of inertia because the mass is, on average, farther from your axis of rotation. Here's another example. Say a globe consists of a hollow spherical shell of mass m and radius r that is supported by a rod that runs from the North Pole to the South Pole that has a mass 2m. What is the moment of inertia of the globe around an axis that is a diameter of the globe running between 2 points on the equator? So we've got a globe the hollow shell, and then we have a rod running from North Pole to South Pole. And then we're asking about an axis passing through the equator, so that would be perpendicular to the rod, passing through the center of the rod. With moment of inertia, just like mass, if you have multiple masses making up your object, you just add the masses together. The total moment of inertia is just the moment of inertia of the globe plus the moment of inertia of the rod. The globe is a hollow spherical shell, so spherical shell, 2/3 mr squared. And then the rod, we've got a rod with an axis through the middle. That's going to be 1/12 m, it has mass 2m, times L squared. Now notice this L is the length of the rod, not a radius like the other ones. It is the full length of the rod. So that is in this case, that's the same thing as the diameter of the globe. So that's going to be 2r squared. And then we can work it out. So we've got 2/3 plus, what is this, 4, 8 over 12. 8 over 12 is also 2/3. So the total moment of inertia of this combined object would be 4/3 mr squared. Another example, say we've got a uniform rod of length 12 centimeters, mass 35 grams, attached to a hinge at one end. And it's initially pressed up against the ceiling, then released. What is its angular acceleration? Well, you know net torque equals I alpha. If it's let go, what force is acting? There's only gravity. And we didn't talk too much about this, again, when we were dealing with point objects, but it should be fairly intuitive to expect that the gravitational force, we can treat it as though it acts right at the center of mass. I know we just got done with doing planetary orbits, but we're presuming this, unless otherwise stated, we presume our objects are on Earth, so we can go ahead and use mg for the gravitational force. That's the only force providing torque. So torque we've got, and that's going to be acting perpendicular to the rod initially. Should say initial angular acceleration. This will change as the rod falls because the angle that gravity makes to the rod will change. That's acting halfway down the rod. Angle is 90 degrees, so it's sine of 90, which is 0, equals rod around the end is 1/3 ml squared. And so we can calculate the angular acceleration. Mass of the two things, these are both referring to the rod, so mass is the same. One factor of L cancels out, and we get that angular acceleration is 3g over 2L. And since you're given numbers, you can plug them in. 3 times 9.8 over 2 times 1.1, which comes out to 122.5 radians per second squared. And then you could also calculate tangential acceleration of the end. We know tangential acceleration is equal to r alpha. So that's going to be 0.12. No, sorry, the end would be not 0.12. Oh yeah, that is the length of the rod. Sorry, I lied. Okay, the whole length is 0.12 times 122.5. which comes out to about 14.7 meters per second squared initially. Another example, got a merry-go-round, which we're treating as a disk. Its mass 123 kilograms, radius 1.1 meters, has a David of mass 61 kilograms standing on the edge, and mass, so merry-go-round rotating around the middle, we've got a person on the edge, and we've got a force 120 at the edge at one point, 140 at the edge at the third point, and they're both exerted in the tangential direction, clockwise. So again, net torque equals I alpha, and our net torque, we've got force from Christian times the distance Christian is, plus force from Montauk times the distance Montauk is, and then we've got the merry-go-round, which is a disk, 1/2 mr squared, plus a point mass, which is just mr squared alpha. and then we can plug in numbers to determine the angular acceleration. Since they're both in the same direction, I'll just use clockwise. It's positive. So 120 times 1.1 plus 140 times 1.1 plus 1/2, 123, 1.1 squared plus 61 times 1.1 squared, all times angular acceleration, and we can calculate that out. 0.5, 123, 1.1 squared plus 61 times 1.1 squared. Bada boom. So the angular acceleration is about 1.93 radians per second squared. And moving right along, this is another fun one. Find the acceleration of an Atwood's machine consisting of masses m1 and m2, and a pulley of mass m and radius r that can be approximated as a disk. String does not slip on the pulley. So pulley, mass 2 is bigger than mass 1, so we'll say it's starting. Now we did this problem before, but when we did this problem before, our pulleys were massless and frictionless. Now our pulley is a rotating object that we need to consider in what's going on here. So we can start writing Newton's second law for the system, and we want to find acceleration. So for mass 1, what do we have? Well, a feature of this is that if the pulley is not massless anymore, the tensions aren't necessarily the same thing. In fact, they're not going to be the same thing, whereas the tension is the same throughout the string if the pulley is massless and frictionless. So for mass 1, I'll call the upward direction positive. Newton's second law, got T1, M1G. On mass 2, I've got M2G, T2 up, and then on the pulley, I've got T1 acting this way and T2 acting this way. So for mass 1, just have T1 minus M1G equals M1A. For mass 2, I have to make the directions correspond. So if M1 goes up, M2 will go down. So I need to call downward positive for this one. And then for the pulley, I need to write the rotational version of Newton's second law. So net torque equals I alpha. Mass 1 going up corresponds to M rotating clockwise. So clockwise torque needs to be positive. That's from T2 times the radius of the pulley. And then in the opposite direction, we have T1 times the radius of the pulley. And that's equal to I alpha for the pulley. And now we know it's approximated as a disk, so that's going to be 1/2 mr squared alpha. But we know that this alpha is r times alpha is the tangential acceleration. So alpha is a over r. And these a's are all the same. The linear, if the string doesn't slip, that means the point on the edge of the pulley is accelerating at the same rate as each of the masses. And then we have 3 equations and 3 unknowns, and we can solve for stuff. And you may notice r's all cancel out from this here equation. And if we add all 3 equations together, then T1 goes bye-bye, T2 goes bye-bye. On the left side, we have M2G minus M1G. And then on the right side, we have the sum of all the math. Well, we got M1 plus M2 plus 1/2 M times A. So then our acceleration, M2 minus M1G over M1 plus M2 plus 1/2 M. And that's going to be the acceleration of each of the masses.